Hi, y'all. We have learned Ohm's law, which states that voltage is equal to current times resistance if we're talking about circuits. And we've also learned how to calculate power for some elements in circuits. For instance, we said that the total power in a circuit, P, is equal to current for the circuit times voltage for the circuit. So today we're going to learn what happens when we put resistors in series. This is something that we did a fair amount in lab when we were dealing with the light bulbs, but now we're going to see how to actually calculate some current values. All right, I'm going to see if I can get there quicker. Yes, good. Maybe I'm learning something. Okay, so I've got here a nice, beautiful picture of a waterfall that I took myself. Let's get rid of my head. Okay. And if you guys remember back, when I introduced the concept of potential, that's capital V potential, I said that potential had the same role in electricity that height does when we're talking about gravity. Thinking about that, as this water falls down from maybe right up there, as the water falls down from there all the way down to right there, it goes through a series of height drops. Right up here at the top, we had a fair amount of potential energy for that water. And then what happens is, as this water goes down and down and down, what happens? Well, that water should be getting faster and faster as it drops. Now there's a series of drops. So there's one right there, there's one right there, there's one right there. It's as if we've got a bunch of steps that are happening as this water drops through. All right, that's a nice picture too, but I didn't take that one. That's a lot of drops. All right. So if we look at this circuit, these two resistors here are similar to those height drops that we had for our waterfall. We start out with this battery. I don't know, maybe it's a 9-volt battery, and so maybe I've got a positive 9 volts on the positive side, and then on the negative side, maybe it's 0 volts. All that really matters is that I've got a potential difference of 9 volts there. So starting out at the positive side, I've got 9 volts worth of voltage. Some of that voltage is going to be used up right here in resistor 1, and then some of that voltage is going to be used up right there in resistor 2. So this is just like if we had a height drop for water, across our first thing, and then we had the water kept going and then dropped a little further across our second thing. Now, one other thing I want to point out here is that all the current that leaves the battery must flow through each one of these guys. So my current through resistor 1, it's got to be the same thing as my current through resistor 2. It's got to be the same thing as my total current coming from the battery. All right, awesome. Okay, I need to clear all that mess. Okay, clear all. Go. All right, so what do we have here? Well, if we take a look, we notice that just like we said that we start out with some voltage, and then that voltage is going to get used up across resistor 1, and then the rest of it's going to get used up across resistor 2, so that the total voltage there across the resistors has got to be equal to the voltage supplied by the battery. Well, if we keep going now and we remember that, we remember Ohm's law that V is equal to IR, then we can use that guy, we can fill it in, just like it does there, IR1, the currents are all going to be the same, plus IR2, there we go. And then what's total voltage equal to? Well, that's just I times total resistance. Or what we notice here is that, hey, I can look at that and I can eliminate all the I's because I've got I in every single term. I is in every term, which sounds really bad, right? That sounds like whole grammar. I is in every term. Okay, now I'm really not hearing anybody laugh at my jokes, so this is even worse. All right, anyway, this gets us to a formula for how we figure out equivalent resistors when we've got more than one resistor in a series. So these guys just add together. So that's pretty cool. Clear this, and we'll move forward. At least we will try to move forward. There we go. Okay, we got a problem here. Our problem says that we've got a battery that has a 100 ohm and a 200 ohm resistor connected to it in series. 30 milliamps worth of current runs through the 100 ohm resistor. What we're supposed to do is find the current through the battery, find the voltage of the battery, find the voltage drop across both resistors, the voltage used up across both resistors, and also find the power used by the 100 ohm resistor. All right, so what I'm going to do here is I'm going to try to draw my circuit. All right, call this R1 and this R2 here. That's my voltage that's being supplied. Now it says that what I've got some current there that's going through resistor 1, but if you notice, if I've got current through resistor 1, well, that current's got to come from somewhere. It's got to go all the way around because we've only got one place for the current to go. All the current that comes out of the battery has to go through resistor 1, has to go through resistor 2. So this tells me that my total current, this tells me that my total current is equal to I1. Well, that's going to be the same thing as I2. And I1, of course, was 30 milliamps. It's 0.03 amps. Awesome. Okay. All right. So what was next? We've got that the current through the battery knocked out. That was one of our goals. The next thing we need to figure out is, well, what is my total voltage? What is that? Well, I know that total voltage is equal to I total and R total. That's Ohm's law. What's my total resistance in this circuit? Well, that's just the two resistances summed together. This is 100 ohms plus 200 ohms. What's that equal? That equals 300 ohms. All right, so awesome. Now I can figure this out. So it says that my current is 0.03 amps. And I've got 300 ohms is my total resistance. So what does that give me? That gives me a voltage of 9 volts. It's like somebody had that planned. So I've got a 9 volt battery basically supplying the current for this circuit. The next thing that I was asked for is, well, what's V1 and also what's V2? All right, so V1 is just going to be the current through resistor 1 times the resistance of resistor 1. So 0.03 amps times 100 ohms gives us 3 volts. All right, and I think you can guess what that means, that the voltage across resistor 2 is going to be not 2, but 6 volts. Oh, okay, well, 3 plus 6 is 9. That makes sense. Good. The last thing we were asked for was the power used up by resistor 1. And we can just pull out one of our 3 power equations that we have. We'll use this one, P is equal to IV. Specifically, I've got to use the current through resistor 1 and also the voltage that's being used up by resistor 1, the voltage drop across resistor 1, that's 3 volts. I get 0.09 watts as my answer. Okay, and we could continue to figure out the power used up by 2 and then the total power supplied by the battery. If you're interested in that, I will let you investigate it. There is another example problem following this one. Let's see here real quick. So there's another example problem here, which I will let you guys read through yourselves because we've got all the work right there. And oddly enough, it looks a lot like what we just did. These really aren't that bad with just resistors in series. Once you've done one of them, you've more or less done all of them. All right, I'll talk to you in a minute about parallel resistors. Oh, hi. Yeah, sorry.